All right, let's dive right in. Today, we are tackling the really high-stakes science of space weather forecasting. We're going to look at the huge challenge of predicting exactly when a massive solar storm is going to slam into Earth.
So just imagine you get an alert that says that a billion-ton cloud of superheated plasma is on a direct collision course with our planet. Figuring out precisely when it's going to arrive isn't just some academic puzzle, it's absolutely critical for protecting, well, pretty much everything our modern world runs on. So how in the world do scientists do it?
Well, the thing we're worried about is called a coronal mass ejection, or a CME for short. Just think of it as one of the most violent things the sun can do. Its upper atmosphere, the corona, just suddenly erupts, and it launches this enormous bubble of magnetized gas out into space at mind-boggling speeds.
And if one of these is pointed at us, the consequences can be really, really serious. We're talking about knocking out communication satellites, messing with GPS and other navigation systems, posing a real danger to astronauts, and they can even overload power grids right here on the ground, causing massive blackouts. So the stakes are high. How do we see them coming?
Okay, so our main tool in this whole cosmic detective story is a pretty clever concept called the drag-based model, or DBM. It's one of the go-to methods for predicting a CME's arrival, and you know what? The core idea behind it is actually surprisingly simple.
The whole model basically boils down to this. Once a CME gets far enough away from the sun, its speed is pretty much controlled by one thing: aerodynamic drag. It's constantly plowing through something called the solar wind, which is just this non-stop stream of particles flowing out from the sun. You can think of the solar wind as a permanent headwind, or sometimes a tailwind, for the CME.
And the logic is super straightforward. If a CME is moving faster than the solar wind around it, that wind is going to act like a brake, right? It'll slow the CME down. But if the CME is moving slower than the solar wind, it actually gives it a push from behind, speeding it up. So over time, the CME speed tends to kind of normalize and match the solar wind.
So if you want to cook up a prediction, you just need a few key ingredients. You need to know the CME's initial speed and how far it was from the sun when it started. Then you factor in the speed of the solar wind itself. And finally, you add this value called the drag parameter, which is basically just a number that represents how much that solar wind is going to affect the CME. You plug all that in, and boom, the model spits out an estimated arrival time.
But here's the thing. That simple model, which first showed up around 2007, was really just the beginning. It was like the spark that ignited a whole new field of research, with scientists jumping in to build on the idea and make it way more powerful and a whole lot more accurate.
And you can see that right here. This flowchart is basically the DBM family tree. That one idea from 2007 quickly branched out into all these different specialized models. You can see how researchers went down different paths, trying to better account for things like the CME's shape, or how it interacts with the solar wind. Let's dig into a couple of the most important upgrades that really helped crack this case.
Now, those first models were a great start, no doubt about it, but they had some pretty obvious blind spots. Scientists figured out pretty quickly that they needed to get smarter, especially when it came to two really crucial things: the actual shape of the CME and the fact that all their measurements had some built-in uncertainty. So here was the first big problem. The original DBM was a one-dimensional model. It was treating this gigantic, complex, three-dimensional cloud of plasma as if it were just a single dot traveling in a straight line. It was only tracking the very tip of the CME.
So what's the solution? Well, you give it a shape. That's where models like ELEvoHI came in. They took the DBM and stretched it into two dimensions. They started treating the front of the CME not as a point, but as an expanding ellipse. And this was a massive leap forward. Suddenly, you could predict its arrival at any point along its huge leading edge, not just at the very center.
Okay, so that took care of the shape problem, but there was another challenge still hanging around. All of those initial numbers you plug into the model, the speed, the location, they're all based on observations. And in science, every single measurement has some level of uncertainty. There's always a little bit of wiggle room. So making one forecast based on one single set of numbers, well, that might not be all that reliable.
And that is what led to the development of what are called probabilistic DBMs, or PDBMs. So instead of using just one best guess for the CME's starting speed, these models use a whole range of possibilities. They run the simulation thousands and thousands of times, each one with slightly different starting conditions. So the result you get isn't a single arrival time, but a much more realistic probability forecast that shows you the most likely window of arrival.
This table here does a really great job of showing the progress side by side. You can see the basic DBM on the left. It assumed no shape, and it treated the solar wind and the drag as constant, unchanging forces. But then look at the advanced models on the right, like ELEvoHI 2.0. They account for a complex, deformed shape, and they recognize that both the solar wind and the drag it causes are constantly changing as the CME travels through space. It's a huge upgrade.
But even with all of these incredible advances, the puzzle is not completely solved. Not even close. There are still some major challenges, some really big unsolved mysteries that space weather forecasters are working on as we speak. For one thing, we know CMEs don't always travel in a perfectly straight line. They can get deflected by the sun's complicated magnetic field and kind of veer off course. The current models, they don't handle that very well. They also really struggle with what happens when you get multiple CMEs launched one after another, and they start interacting out in space. And at a fundamental level, they all still rely on some very simplified, idealized ideas about the CME's actual shape and the forces acting on it. And the stakes for getting this right are just incredibly high. I mean, listen to how the researchers behind our source material put it. They said that a low success rate leads to a lot of false alarms, and a big error in the arrival time means we might take really costly preventative measures, like shutting down parts of the power grid for way too long.
Which really leaves us with this final big question. We've made these huge strides in being able to predict these cosmic storms, but as our world becomes more and more dependent on satellites and space-based technology every single day, you have to wonder, can our ability to forecast the weather in space actually keep pace with the ever-increasing risk right here on Earth?